Uh, and dear colleagues, I'm glad to announce our today's speaker. Professor Thomas Fiedler will tell us about polynomial 1 cocycles for knots and equations for tangles. Let's welcome.
Okay, thank you, Vasil. First of all, thank you very much to the organizers and especially to Vasily to invite me to give a talk at the seminar. It's a honor and a pleasure for me. So in my talk, I want to advertise a new approach to combinatorial knot theory. So that means the study of knot diagrams. This is an ongoing project, and I hope something fine will come out. So this is an increasing number of collaborators, which I mentioned some on the blackboard, and so it's just developing. So if you are interested, it's just join. You are free to work with us. So what is the classical approach? The classical approach is the study of knot diagrams. So everybody knows what is a knot diagram. But on the other hand, it's well known there's this famous result of Whitehausen, which tells us that the peripheral system is a complete invariant. So this is not a practical thing. So, but morally, it tells us that if we study even knot diagrams, we always have to add a base point, a meridian, and a longitude. So that's just necessary. So from the very beginning, we will, instead of what usually these closed knot diagrams, we consider long knot diagrams. So that will always be long knot diagrams. That means it comes from infinity, then there is a knot, and it goes to infinity. And it is well known that this is equivalent. So if you have two knots, you can make them long, and the knots are isotopic if and only if the long knots are isotopic as long knots. So we don't lose anything, but we gain a base point. It's a point at infinity because nothing ever moves over this base point. This is a very useful thing. So on the new page, what will we replace long knot diagrams? We replace it by one families. Of long knot diagrams. Okay. So how knot diagrams or long knot diagrams are usually studied. They are studied by the Rademacher moves. So what are the Rademacher moves? So we consider the modular space of all long knot diagrams. Oriented, of course. It's always oriented as long as it comes from infinity, goes to infinity, and it's not diagrams. We fix one for all a projection in the plane. Everything is oriented, and we consider all diagrams with respect to this projection. So then in this modular space, we have the discriminant of non-generic projection. So it has a stratification. Everything is infinite dimensional, of course. Also, this is just codimension 1 in this modular space. So these are the non-generic diagrams. An ordinary diagram has just ordinary double points in the projection, and everybody knows. And these are the non-generic diagrams. So what are these sigma 1? Sigma 1 are just, we see in the projection, either a triple crossing or an autotangency or cusp. Okay. And passing through such non-generic diagram corresponds just to the Rademacher move. So from the very beginning, we will eliminate the Rademacher 1 moves. So no cusps. So the projection will always be an immersion. That's easy to do. If we have a long knot diagram, we have two, can associate two numbers, the rise, V, G, and the Whitney index, and D. So this is just massive event of D1 of D0. So you count the sum of the signs of the crossings, and this is just the homotopy class of the immersion in the plane, so the Whitney index. And it's well known if you have two long knot diagrams for which are isotopic, and these numbers are the same, then in fact there's an isotopy without Reidemeister 1 moves. This is called regular isotopy. So we can completely get rid of Reidemeister 1 moves. Starting from here, everything will be regular isotopy, and this is this is still a whole generator. Okay. So what we have on the other side, of course, now is sigma 2. So we consider families of long knot diagrams. So we have to study a higher Reidemeister move. So sigma 2 contains, we see ordinary quadruple crossing. You see an old tendency where branch passes, and of course we have transverse intersections of strata of codimension 1. For example, that, or another Reidemeister 3, and some other minor stuff. And we have only to deal with these three types. We show something behaves well by passing in a one-parameter family through such point in strata of codimension 2, then everything is fine. So what usually,
whenever I see such codimension 1, codimension 2, and so on picture, I think of groups G and K. I think of groups when we pass through a crossing. We have codimension 1 for
of course. Yeah, you can see that if you have generators in groups and you apply the generators, you go through such strata. Yeah, that's. And the braid group,
let's try to write a group. Let's try to write a group. Let's try to write a group. Yes.
Yeah. But here you are just on the topological level with no group structure. So what are we doing usually with Reidemeister moves? So we have this M, and we have here this sigma 1 inside. And we have a diagram G, we have another diagram G prime. Okay? We associate something to this diagram. Some number, some group, or whatever. And some polynomial. And in reality, this is just a zero code chain. We associate something to a diagram, this is a zero code chain. And what we want, it is a zero code cycle. What does it mean? It means if these are in the same component and we find a path that goes one to the other, then this will be the same. So what evidently, if we are here outside of the discriminant, then nothing will happen. ED will just be the same. And here we come to the Reidemeister move. So we have just to prove if we make a Reidemeister move from here to here, it does not change. From here to here, it does not change.
Yes. So, in order to have an invariant, you are trying to construct co-cycles. So you have co-chains and you want to have co-cycles, and it is commutative. It may have some nice values, but if it is so, our approach is to do group theory. Let's try how we may amalgamate co-cycles and groups, because groups may be non-commutative, and instead of writing A plus B equals C plus D, we write A times B equals C times D, and it gives more information.
Yeah, you see here, we see, and it's commutative. You see, if we take this path, we take this path. So the order of this Reidemeister move has changed, but it's still the same number. It's the same invariant. So this is what's usually done in classical knot. You construct zero code cycles. And what we will do now, we construct one code cycles. Here we have the same end. We have again our discriminant, sigma 1. We have our two diagrams, D prime. And we assume they are in the same connected component of M. That means they represent the same knot. Then we find an isotopy, a path S, And we will associate something now not to the endpoints of this path, but to the path itself. So we define I of S. Okay. And what we want, if we take another path, which is homotopy to that, as prime, we want that this gives the same thing. So if we have this property, then we have that I is 1%. But we don't want any 1% we want combinatorial 1%. So E is combinatorial. If it is obtained by discrete integration along the path. If discrete integration along it. Now, what does it mean? We see here a finite number of Rademacher moves. So E of S, which is the sum over Rademacher moves, R moves in S, some sign, and some conclusion of the move. We associate something to this Rademacher move. Okay, it will be what we will later associate. It will be singular tangles. So it will be a linear combination of singular tangles. Okay, and this is a combinatorial one-foot cycle. This is a combinatorial one-foot cycle, and how we will use it? We will use it to define the tangle equation. Great, now that. Say that. Tangle equations. So we are on this side. So let me make again this picture. So here we have our D. Here we have our say D prime. And we take a long auxiliary knot diagram K. K is auxiliary. We choose it. Long knot diagram. One which we know well. Okay. And we take as a product, we take KD. So it means here we have K, and then here we have our diagram D. Looks like that. So we take this, so here we have KD, now here we have KD prime. And what we can do, we make this K small and we push it all along D to the other side. So this is called push D. This is an isotopy, regular isotopy, which end at Z. Okay, it's now on the other side, we commute it with D. So we consider this in this space. This is the push, KD, and we come here to DK. So assume that D and D prime are in the same component of the moduli space. So that means here's an isotopy gamma from D to D prime. So here we call it isotopy K gamma. So we just take the isotopy from that to D prime, but we have always the K in front of it. So it's the same isotopy. And here we have an isotopy. So here we take the push, of course. K prime, and come here, comes the D prime K. And here we take the same isotopy, gamma, but K is now on the other side. So this here will be gamma K. Okay, so we get a square. We make Z. So this is a loop. So we have a loop.
Yes, and the main idea is to make it non-commutative.
Yeah. That's a loop. And what is important about this loop? This loop is contractible. So we have a contractible loop. Why? Because at each moment we make other isotopy, we can make the push. Okay, D here changes dk to from D to D prime, but at each moment we can push K through it. So we can fill it by this push. Though we have a square, so that means this loop is homotopic to 0. So if we have a one-foot cycle, we can evaluate it on the boundary of the square, and it has to be 0, because a one-foot cycle, the loop is contractible, so it has to be 0. So what does it give? It gives us that E of push KD. So then here we go in the other direction in the loop, minus E of push KD prime. This is equal to what? This is equal to, we bring this on the other side to E of K gamma minus E of gamma K. Okay. And this is the form of the tangle equation. So this on the left side, we can calculate. We see K, D, D prime, we can calculate this. So this here can be calculated. And these here, we don't know anything. We don't know if gamma exists. If D and D prime are not the same node, then gamma will not exist. But we know it has this form. And from this form, because we see the moves here in gamma and minus gamma, the randomized moves are just the same, with opposite sign. But K is at a different place, and this will play a role. So here we get an equation. Something which we know should have this form. And this is sometimes enough to rule out something, but it has also another good aspect. So let me continue at this side. We were here. There's another problem in knot theory, which is even the most difficult one. Assume that we cannot distinguish. Assume we cannot distinguish D from D prime. So all our invariants are the same. So then find the other. Which connects them. So this is such a hard problem that's almost never mentioned. So there are very few things known. It's known for the trivial knot. Trivial knot, you can find that as a and I know only one general side, which tells you the side of October 2009. The schedule, you can order the randomizer moves. You can make first all randomizer 2 moves, which increase the number of crosslinks, then only randomizer 3, and then you can make only randomizer 2, which decreases the number of crosslinks. So it gives some structure on this isotopy, but it's not constructive. You don't know which moves you have to do, when you have to stop, and so on. So it just gives some information how the isotopy looks like. So if we go to the other side, if the tangle equation has no solution, this implies that D and D prime are not isotopic. Not isotopic first. So we have distinguished that. In particular case, if this thing here is 0, sometimes it happens. I will explain when this happens. If E gamma minus E gamma K is 0, then we know this thing here is not a list. Then we will push and we not invariant. So not invariants are just a very particular case of the tangle equations. In general, this thing is not 0, and we get an equation. If it has no solution, we know they are not isotopic. But in some cases, this is 0, so we know that this is not invariant. So not invariants are particular cases. And if the tangle equation has a solution, so we find E gamma. has to then it gives us quantitative information about the isotopy. About any gamma which connects D to D prime. You see, the left side here does not depend on gamma. So, in fact, this information here, E gamma, will depend only on the endpoints. Because E gamma depends only on D and D prime. So, we will see this E gamma, this linear combination of singular tangles. And they tell us somehow which Reidemeister moves are in this isotopy gamma. And in very simple cases, this is enough to recover a gamma. Very simple cases. E gamma determines. We can recover the isotopy. So, before going on, let me tell you a bit about the results. There aren't yet very many results. So this was here the difference. So we can now go on about results. So there's a one code cycle. One right code like that. It's a one code cycle. It lives in Z1 plus M. So this is a two cable of frame number.
So what in the subscript R? What's in the subscript?
Regular.
Okay.
Regular. Because as I said, we are always in regular. So in particular, everything is framed, and even more than framed. Framed is just Rice. He has Rice and Whitney index. It's a bit stronger even than framed. So everything is framed. So we take the two cables of framed donuts and it lives the values in the one polynomials. That. Okay. This one code cycle was programmed by Bucha and Sam. And the tangle equations. Yes, this one code cycle is the tangle equations. Distinguish 942 from Merle, and which has the same Homke and Hoffman equation. Same. Okay, but on the other hand, we know from Morton and Fromberg that the two cables that Homke with two cables also distinguish. So it's not really new. So, but I'm very optimistic that it will give something at the end. So, because what I will tell you today is the upgrading of this by 4 times. There are 4 flows over it, 4 upgrades, different upgrades to this code cycle. And so let me first say what is the goal. So the Holy Grail. How's that written? Shows the non-invertibility of the conveyor knot. conveyor knot. Okay. So what is a conveyor knot? Conveyor knot is an 11 crossing knot. The 11 crossing knot. With the Alexander polynomial 1. So it's the same as that of the trivial knot. So whatever you know with the methods by Potter taking irregular coverings, everything breaks down. There are no covering methods with this. It's just like the trivial knot, and the trivial knot is invertible, so you cannot show. So it was proven by Cooper that the not invertible. Just how he did it. How he did it. He did it in this way. There is a simple squaring root. ML, M11. It has 7,920 elements. And it admits no automorphism. No automorphism. Or no automorphism that inverts a certain element, an element G of order 11. Okay. And then if you consider the fundamental group of the complement of the conveyor knot, so there is a unique epimorphism to M11, which brings the meridian to G. So that means C cannot be invertible because you should have an automorphism of M11 which inverts this element. So, but to do this is done with computer programs. And he has nearly 40,000 different tests to consider. So it's extremely difficult. Okay. So if we can do this in a much simpler way, it really would be a big progress. So why I'm optimist? By the way, in the same paper, he shows that if Vassiliev invariants do not distinguish the orientation of knots, then they even fail to distinguish non-oriented. So we are very, very far from the solution of the problem. Oh, I'm optimistic because of these upgrades. So what we do is we upgrade. This will I tell you later. So it's to one could cycle as let me call it red, plus black red X. There's a new variable X, which lives in, if one could cycle in M2, the values now in H0 of M plus that X plus H0 minus that. But what are these spaces? So M plus, or 2, like here 2, is two cables of long knots with exactly one double point, which has a positive sign. The space, moduli space of two cables of long knots with exactly one ordinary double point. So it's not single element. with sign plus. Double points. Here with sign minus. Double points become a sign. These double points, they come from our one-put cycle. So we move something, and at some moment we have to make singular. But it comes from a crossing. And the sign of the double point just remembers the sign of the crossing from which it comes from. Sign of double point.
So I don't see the superscript. All are regular, and
Yeah.
what are the?
This is red, black, red. So I will explain what it is. So we have the one-put cycle for two cables splits into two one-put cycles, and the value splits still again into two one-put cycles. And instead of having polynomials, we have now linear combination of isotopic classes. So what does it mean? It means it's a combination with coefficients in a polynomial ring of isotopic classes of two cables of long knots with a double point. Okay? So this is in certain cases, this if I apply it on push, two K, of course, I have now to double K and to double the diagram is an invariant. Is an invariant. Of course, there are tangle equations, but let us consider the simpler case is an invariant just if the rise of K is 0. All you need in diagram with rise 0, then we know that this thing will be an invariant. So why is this very promising? Why is it promising? Because if we have the double point, say here's our double point, plus. So we have two operations we can make. I'm thinking preserving smoothing. We can bring it to that. Okay. If we here started with a two cable of a long knot, this here will be a two string link with a closed component. With an addition. Closed component. But we have another operation. We have crossing field. So we have here our plus, a double point is plus. That's a double point. And we see it came from a positive crossing. So we just replaced it by the negative crossing. That's now a recrossing. So this is again a string link, a two string link. But it's no longer a two cable. You know, we have the two cable of a long knot. And we change one crossing in this two cable. So each crossing here of our original knot becomes four crosses. You just change one. Say, for example, that's no longer a two cable. Okay. So there, the incompressible torus in the complement has disappeared. So this is a two string link, which is no longer a two cable. This is neither this, which is no longer a two cable. Okay. Why is this good? Because there is a very nice paper by Dugin and Fiedler. I think it was 2005 or something like that. Which shows there are finite type invariants. There's a finite type invariant of degree 7 for two string links, which can detect non-invertibility. What's the difference? Of degree 7, so it's not a high degree. One can write it explicitly of degree 7, which can detect the non-invertibility of two strings. two stringlings which are not two cables. Otherwise, you have a series of invariant which can detect the orientation. Things which are not two cables. So where does it come from? Why it works? Gaussian invariant do not work for knots, but they work already for two stringlings. Why is that? The reason is very simple. So what means changing the orientation? So if you change it, you have here the stringling. So what you have to do, you have to make here the flip. You make a rotation around this axis by pi. Okay, which comes to that. Okay, and then you have to change the orientation again. Then orientation. So now it looks like that. So this is the inverse. So the stringling is invertible if this thing is isotopic to this S stringlings. So if you forget about one string, if you take a one tangle, this is just the invertible of a knot. So long knot, the knot which corresponds to the long knot is invertible in the usual sense, if and only if it is invertible in this sense. Okay. So so let's see, what does it mean? If we have a crossing, this is the z-axis. We project in the xy plane, and here are two branches. So say branch 1, branch 2, which are projected in a double point. So what happens if you make this flip? If you make this flip, it will look like that. That axis goes now like that. Here we have 1, and here we have 2. The projection is here. So it means here, if there are different components, see, this is component 2, and this is component 1. So we see the overcross is in component 2, the undercross is in 1. We make this, the overcross now is in 1, and the undercross is in 2. The undercross is in 2. So the overcross and undercross has changed the component, and that's enough. This is a big change. And therefore, Gaussian invariants can now detect orientation change. So this makes it very optimistic, because what we get is this construction, if I tell you, we get two stringlings. And of course, if you take the inverse knot, these two stringlings also will be inversed, and with the double point now is here inverse. And we have just to show, if we make our orientation preserving smoothing or the crossing change, that the corresponding two stringling is not invertible. So that has changed when we make our flip. And this invariant of Gaussian of degree 7 could perhaps do it. So this is what we have won with our construction. Okay. So let me go on. So how to what to do. So let's come to the construction of the one concept. So the most one combinatorial one concept. The most important thing is, of course, the point of the crosses. It's just, and the Reidemeister moves, Reidemeister 3 is the most important, the Young-Baxter equation. And here this corresponds to the tetrahedron equation. Because if we make it generate, we have 6 crossings. So this is just the 6 edges of a tetrahedron. And we have 4 triple crossings if we go around it. So this is the start of codimension 2 and sigma 2. So if we take the normal disk and we take the meridian of the normal disk.
You see, and this is exactly the main relation for our groups GN3, I think. and I bet our groups should be a non-commutative version for your equations for this cocycle. So I bet there should be a non-commutative version of that.
Yeah, I will. There is non-commutative tangle equations for notoids. I will think about this a bit later, perhaps. So we have to consider what happens if one parameter family goes to that. So in the unfolding, so in the normal disk, this sigma 2, the point in sigma 2 in M. So it's 2 dimensions. What do we see? We see again the same thing. But here each thing is a triple crossing. And there's one branch which goes aside. Okay. So this here is now no longer in the plane, it's in this infinite space, and the two disks, which is orthogonal to that, transferred to that. And the Tetrahedron equation says if we go around this, the meridian, we associate something to a triple crossing. These are 8 triple crossings. We see 8 triple crossings. I will give it a little bit more detail with the later. 8 triple crossings. But we associate to it, it should cancel out. So usually what people do, we see each of these triple crossings twice. So these are just strata of sigma 1. We define a co-orientation of the strata. So we have just to fix, in one case of a triple crossing, so we fix it, definition, once for all. If we take a positive triple crossing, so it means all 3 crossings are positive. And we come from here to sigma 1, sigma 2, sigma 1, to sigma 2, sigma 1, sigma 2. We see this is sign plus. So that's the convention. We say this is a positive direction. That means we make a co-orientation on the strata. The strata is infinite dimensional, but co-dimension is 1. We say this is the positive direction. So we come here to that. We see each of these twice. If we have our triple crossing here, we see it again the same, but this thing here is now exactly on the other side. Okay. Comes like here. It comes like here. Okay, we see it twice, and we see it with opposite sign. So if this was a plus here, of course, if we go along this, here it comes from minus. So what usually people do is they take an invertible matrix or invertible operator, which they associate to each of these triple crossings. And if we come to the triple crossing with opposite sign, they take the inverse operator, and they take the product of these operators, and that should be the identity. So this is the usual Tetrahedron equation, and it has many solutions at first, I think, found by Samolotchikov. But it's of no use for us. So we will use it in a quite different way. We will use the combinatorics of the Tetrahedron. First of all, one can show that it's sufficient to find a solution of the positive tetrahedron equation. The positive tetrahedron equation so all crossings are positive. Okay, so you can see like that. So we have the highest strength, then the coming strength under it, the height I call it 4, this one 3, then came strength under that 2, and then the lowest 1. So all crossings are positive. So starting from that, I can make planar pictures. I have not to draw the crossings because there's a unique decimalization to a positive crossing. Okay. So what would be the nicest thing? The nicest thing would be we associate something to that, and it should be the same as that, and they cancel out together because signs are different. So the trivial solution of tetrahedral equations. Each strata cancels out with itself. Each strata cancels out with itself. It goes to be twice. The diagrams are different, let us see twice. So unfortunately for knots, there is no such trivial solution which is not trivial. But it's very different for closed braids. There are interesting.
You see, our GMK approach gives a lot of non-trivial solutions in the case of just braids.
Then give you a non-trivial solution of the Taylor equation for knots. But in the case, so trivial solution by definition is each this cancels out of that, and that cancels out of that cancels out of that, and so on. Okay, and there's no trivial solution for knots, which is interesting. Okay? But there are trivial solutions for closed braids, which are interesting. So therefore, I make a parenthesis about closed braids. It's an interesting trivial solutions for closed braids, which are not. I already need those knots. Okay. So how they are defined? So if I have a randomized string move of a knot, so I take the Gauss snapper. Gauss snapper of string. Because it's not, it's a circle, it's oriented circle. And there are three crossings. A crossing is always in a circle. Crossing goes from the undercross to the overcross. I make an arrow. So here would be an arrow from here. Is this the undercross of that? Overcross. So here overcross, here's the undercross. And say here I make it like that. So this is the undercross, overcross. So it's a triangle with three arrows, which are oriented arrows, and there are just two possibilities. I call this a possibility R, and this is a possibility L. Goes like that, and this goes like that. Here it goes to the right, goes to the left. So it cannot be an oriented triangle, it wouldn't be a Rademacher human. Okay? And to each crossing, say I have a closed braid. A closed braid is just a knot in the solid torus. Okay. Closed braid is a knot in the solid torus. And we can, of course, ask the knot problem for these knots in the solid torus. So it's well known if I have two closed braids in the solid torus, which are isotopic as knots, then they are isotopic as closed braids. And if they are isotopic as closed braids, then they come from two braids which are conjugate. Okay, so the isotopy problem for knots in the solid torus which are closed braids is just the conjugacy problem. Isotopy problem. Conjugacy problem. Okay, and the conjugacy problem is solved by Gasser's argument. But Gasser's algorithm solves it completely. It gives also the conjugating braid. So it means we find really the isotopy. The whole problem is solved. But it's of exponential complexity. And it's still an open question. Open. If the conjugacy decision problem has a polynomial solution. The solution in polynomial time. So it means just you have two braids and you want to say are they conjugate or not without finding the conjugating braid. Okay. So this is still an open problem. So it's still an interesting question. So So what we do, we construct one foot cycle. We construct one foot cycle. So we have this Gauss diagram. So if I have a crossing in Gauss diagram, the crossing Q oriented, I can consider the loop which goes from the overcross to the undercross. This here is a loop. Okay, and I take, because I'm in the case of closed braids, this loop will represent a homology class in H1 of V. So this loop I call it as 2. The loop, we call it 2. The homology class is in H1 of V. H1 of V is that. And we know this homology class is not 0, neither n. So if that not, what will be n? It cannot be 0 or n. It has to at least go once around in the solid torus. And moreover, we have this property, whatever we take of smoothings of crossings of these things, this loop will always be not homologous to 0. Each loop in V, which comes from smoothings of crossings, from orientation observing, of course, smoothings of crossings, smoothings of beta is not homologous to 0. It's not 0 or n. So it's always, so it lives from 1 up to n minus 1. So this is very important. This makes the difference with knot theory. The only difference that for knots, if you take the n cable and we consider it in solid torus, 0 an can appear. And it makes a lot of problems. But for closed braids, not. So let's come back to that. So we have a homology class associated to each of these arms. So this is the Rademacher 3 move, and say we take n equals 3. So you can think of n equals 3k and everything multiplied by k, just for simplicity, let's take n equals 3. So we want that this here, so this here will be a 1, this here is a loop will be a 1, and this here will be a 1. So we have to associate to that here. This from the overcross, this is a 1, this here will be a 2, this will be a 2. Okay? And we consider only Rademacher 3 moves where the homology classes of the 3 crossings are like that. Okay. And if we consider the tetrahedral equation, so it looks like that. So if we had our triangles and we have another crossing, so you have our triangle and there are 3 other crossings. And the 3 other crossings say if this crossing was like that, we have here crossing 2. On one side, here we are in the same equation as on the other side now. The other side now. Then what happens to this crossing Q? It can become that 1 foot or 1 head of the arrow slides just over 1 edge of the triangle. So it could be that. It could be that could be slide over that. It could be that. It could be that. Yeah, that slide over that. So at 1, 2, 3, 4, it could be that. Slide over. Okay. So what we consider now, we consider all Rademacher 3 moves with that. We define a weight of dv1. So it's this Rademacher move P of this time. dv1 P is defined as the sum of the signs of all crossing Q, which are like that. So this was 1, this was 2, this was 2, and here I have my crossing Q. Which goes like that, and which has the homology class 1. It's a 1 crossing. Okay, that crossings can exist. So let's consider what would happen if it moves here. So I come back to this triangle. So let's make it here in this one. So we had our Q, which was like that. It was 1. So it looks like that, and we have a 1 here. You see, we have here a loop. That goes to that, that goes to that. That's a loop. And this loop would be 0, because that here is 1, that here is 1. So this loop here would be 0 loop. As we have mentioned, it cannot appear. So it cannot move to that. Could it move to that? To that? You see, this here is a 1. This here was a 1. It cannot move to that. We would again have a 0 loop. Can it move to that? This is here we have 1, we have a 1 again, and so on. You see, this error here is completely rigid with respect to the tetrahedron. So it cannot change. So that means that we can define this weight, associate this weight to all these moves, and we can so this was the weight. We want was was 1, 2, 2, and this was 1. I mean, this is always in the sense I sum up over all crossings, the signs of all crossings, which are like this, which is somewhere. We define B2, B, that is the same, exactly the same triangle, but one is now, yes, 1, 2, 2. One is not like that.
Excuse me, and what is 1, what is 2? What does it mean?
Of the loop which comes from the overcross to the undercross of the crossing.
Okay.
And we take V3. Same thing here as 1. It's rigid. V3 okay, is that. That's 1. That is 2. That is 2. It comes like here, and it has to be 1, or it has to be a 2. That has to be 2. Okay, that is completely rigid. Okay. Then it turns out we have the following thing. We can define the following thing. Gamma. The sum over all triple points P of this form. 1, 2, 2. In gamma. Gamma is a loop. Gamma is a loop. In the modular space of closed 3 braids. And 3. Sin P times x1, a variable, x1, x2, x3 independent variables. So x1 to the power 2 times v1 of p plus the sign of the distinguished product. Oh, I have to tell you, if I have read my specific move, I have 3 crossings and I can distinguish. So we say it's a crossing of the highest branch. So this is the highest branch, 3. This is the middle branch, 2, and this is the lowest branch, 1. It's a crossing of the highest branch with the lowest branch. Yeah, highest branch with the lowest branch, 1, 3. It's a distinguished crossing, D. Then we have the crossing ML, middle branch with lowest branch. It's a crossing 1, 2, and we have the crossing HM. It's a crossing middle branch with highest branch. Okay, so we can distinguish these 3 crossings in a randomized system. That's a very important thing. And somehow the crossing D is the most important one. Because you see, if we would make it singular, so we couldn't no longer move this branch. But for the others, if we can make it singular, we can still move the branch. So this crossing is somehow the most important. And D is just the sign of this crossing. Times x2 to the 2p plus LED times x3 just this. Okay, this is a thing which lives now in Z of x1 plus the minus. So the Laurent polynomial is 3 variables. Okay. We will apply it. The theorem is this is a 1%. Uh, 1%. So it's really a very easy proof. We have also to study that this comes to proof equation, so it becomes too technical. So I will not explain. But in any case, everything what I'm telling here is well written in this my monograph. Polynomial. What is called it? Polynomial valued polynomial one cocycle for knots and closed braids. Knots and closed braids. It's 2019. It's a monograph. So you will find this part, what I tell you, you find this in that. So this here is a one cocycle. What about so how we apply it? So if we have our braid beta, such that beta is a knot, it's a closure as a knot, we just take it's a full twist. We take delta square, delta is gas element, so just a full twist. That means if you push it through the solid torus, just the rotation around the core of the solid torus, and you push to delta square delta. So this corresponds just to a rotation of the solid torus around its core. So this is a loop. Because on the other side, of course, we have pushed it through, and then on the other side, we can bring it without any moves in the initial position. So this is our loop gamma. We can apply Aaron gamma. Is not in range. Adding a footness that doesn't change anything of vector. So how to apply it for invertible? Invertible and non-invertible is exactly as before. If you have your braid, if you have here your braid beta, so what you make, you have to make the flip. You flip it over. Looks like that, beta. The flip. And then you change the orientation. So it just means you read the braid backwards. You read the braid backwards and you close it. So this is the inverse closed braid. So we want to distinguish braid from its closed braid from its inverse. It's complicated because if you take, for example, a home-flight polynomial, for that you evaluate in the Hecker algebra. The Hecker algebra of n strands. So it can never distinguish a closed braid from its inverse, because if you develop in the Hecker algebra, the basis elements are all invariant under that. So for n equals 3, for example, you have that. You have that. And you have that. So this here is sigma 1, sigma 2. And this is sigma 2, sigma 1. So here they are just invariant. Here they are interchanged, okay? But they are conjugate. Just, you see, you could push it on the other side and the rest of the solid torus. Or you can just conjugate with delta. If you conjugate with delta, this comes to that. So these are the same elements. So if you make the calculation, it's a scaling relation in the Hecker algebra, you just will get the same result. So quantum inverse cannot distinguish quantum non-invariant. Even in the Hecker algebra. Cannot distinguish a closed braid from its inverse. A closed braid from its inverse. but we can. Invariant R doesn't. So I've just calculated by hand one example. So I take, yeah, you see immediately one thing. If you take the inverse, if you take the inverse braid, so that's, if you make the flip, yeah, we had that here. That, so this was our Q, which corresponds, which contributes. All the homological marking sign and so on to make the flip are the same. So what changed? What changed? Here was the orientation. You have to make the flip of that, just like that. No, like that. Here, this here will change. This crossing becomes that crossing becomes that, but overcross and undercross change. It becomes this. That. And here, this crossing will change too. We have to flip it over, but then we have to change the orientation, but it will be again in this direction. Okay, this crossing now goes to that. And we have to change the orientation. So it comes to that, comes to that. Okay, and then we have to change the orientation of the whole thing. So now again like that. And what we will see, you see that here contributes to wave 1 clip. And that here contributes to wave 2 clip. So the interchange we want to repeat. So if we have beta close braid and beta inverse. So if they are isotopic, then the loop here, gamma inverse, we're pushing delta squared to that and delta squared to that. These loops are homologous. Okay, it's just the rotation around the core of the solid force. If these are isotopic, then these loops are homologous. So the 1-2 cycle has the same value. And because of this, we know that the value of the 1-2 cycle should be invariant under changing x1, x2. If beta and beta inverse are isotopic, then R of the gamma invariant under x1 and x2 direction. Okay. The change is variables to the same thing. So I just calculate one example. Now I took a knot, but it's not a knot, but because for sure that I have more chances to prove it. So I just hit knot at 817 SS3 braid. I braid just 2 instead of sigma 2. So it's 2 to 1 bar. This means sigma 1 inverse. 2 1 bar, 2 1 bar, 1 bar. Okay. So you know that here is the closure of that is 817. And so I calculate R delta. So delta squared just 1 to 1. Right? And so there are a lot of randomized moves, but it's a really easy calculation. And the result was that. So it's minus 1, 5, 1, 3, minus x1, 3, x2, 3, those 2 times x1, 3, x2, 3, plus x1, 2, 5, minus 1, 2, 3, 3, minus 1, 2, 3, squared, plus x1 minus 1, x2, 3, 3, 3. And you see, immediately by many ways. For example, here's the coefficient 2, and it's not the only one with coefficient 2, and x1, x2 are not symmetric. So we have shown not enough. Notice that we have shown that the quadratic complexity. The number of itemized C move is a linear function of the number of crossings. And the weight is a linear function. For each randomized remove, we have a linear combination of this crossing. So the whole thing is quadratic complexity. Therefore, I could calculate by hand. And so we have distinguished this braid from its inverse with quadratic complexity. So I stopped considering braids at this moment. Was more than knots, but it seems to me still an interesting subject to make a systematic study of these one-code cycles. So each can be calculated with polynomial complexity. Of course, you can then consider bunches of crossings. We take a bunch of 2 one crossings, and this is still could not move over that. And so on. But it becomes more complicated. Formulas will be longer, but still polynomial complexity. If you find a polynomial number of such one-code cycles, which would distinguish all closed braids, you would solve this problem, conjugate decision problem in polynomial time. So it's just another approach. Okay, I just wanted to speak about that. So let's come back to our main subject, the knot theory. So I have to draw a little bit the meridian of the quadruple crossing. Meridian of the quadruple crossing. So I can make planar picture because meridian of positive quadruple crossing. Looks like minus P1. So, and this goes from here to here. So all orientations are like that. So this is the lowest branch, 1, 2, this is branch 3, and this is the highest branch, 4. So it comes to that. Then here it comes to that. Minus 2. This is the sign. The sign, once we have defined the sign sigma 1, sigma 2, sigma 1 goes to sigma 2, sigma 1, sigma 2 is positive. All signs are determined. So minus P2, which looks like that. I will draw it just like that. Then comes to plus P3. I give names to this type. P3, which is like that. That comes to plus P4, which is like that. It goes to that, and comes to plus P1 bar, which is the inverse of this. Note the bar. And so this thing here goes now like that. It's the same triple crossing, but just this branch is moved over. Then it comes to plus P2 bar, which looks like that. It has now to be on the other side. And then it comes to minus 3 P3 bar, which looks like that. This is now like that. Okay. And then comes minus P4 bars. That which looks like that. It goes over that, and it comes back to that. You see the 8 strata which go here around this thing. 1, 2, 3. Okay, so the basic solution is the following. If we have or positive, that here's the crossing D, so this comes to this. So we have seen here the sign was plus. So this here is the positive side, and this is the negative side. This is what's here the rotation of the discriminant. So this is positive negative side. So what we associate to randomize the three move here, this is S3. So this S3 move. Yeah, it's a sine. The sine of K times VD, the sine of the distinguished crossing. Here in our case, the distinguished crossing is positive, times desingularization on positive side minus desingularization on negative side. Okay, so in our case, it would look like that. Here it would be the sine P times positive side is Z minus negative side is Z. And the crossing D becomes singular. Here's a double point, which is plus, because it comes from a positive crossing. So here's now a double point, which is plus 2, comes from a positive crossing. To this Rademacher move, we could associate this combination. Okay. So you see immediately if we make that, we don't need here any weights, points at infinity, and so on. If we make that, you see this strata when one branch goes over everything, or one branch goes under everything. P2, P3 goes over everything, P2 goes under everything. That will not change. That will cancel out with P2 bar. P3 will cancel out with P2 bar. So we have P2 minus P2 bar, P3 minus P3 bar. No contribution. So only when it goes between the branches, so P1 bar, P4 and P4 bar will contribute. So let me show you just, let me just indicate to you how that would go. So let's consider P1. So I will keep that picture. Let's consider P1. So it is a minus sign, we have minus. So here it's on the positive side, looks like that. And this branch goes like that. Up. So it comes from that, and this point is the singular point. Okay. Minus. And here it's the same thing. So here was the triangle. Yes. This is now singular. So this is a contribution of minus P1. Let's consider contribution of plus P4. Plus P4 is here. Plus P4 looks like that. Here I have positive side. And it's triangle, and P4 here it comes over 2. Here it goes something like that. Minus, now I have the triangle that. So here it comes over this 2. And here it goes something. Okay. So here it becomes singular here. Here it becomes singular here. So what do you see? You see this thing here is isotopic to this thing. Just slide it over that. So they will cancel out together. These two will not cancel out together. But there are still 2 other strata. And it will say there 2 will cancel out together on these. And the remaining 2 will cancel out with this. And that's all. So we need 4 strata now that everything will cancel out. And the value of our one good cycle is now in singular tangles. Okay, singular strings. Singular. So, but it turns out that this one good cycle is not interesting because we haven't used all the information, all the base points, the meridian is long, so it will not be interesting. So I have to go faster. Go further, we will use 2 other strata, P3 and P3 bar. We use in addition P3 and P3 bars. And only P2, but T2 minus T2 bar is the answer. So we use 6 of this extra. So for that, if I have a long knot and I have a crossing, say a positive crossing, there are two global types. So this is my thing. Is it like that? You see, if I take the loop which comes from the overcross and goes to the undercross, then that's here. This is here a loop. If I take a meridian of my knot near to infinity, and near to infinity, I see this loop here is not linked with this meridian. So this is the meridian of my knot, my long knot. So I say here Q is the 0 percent. And whatever I do in my isotopy, it will always stay 0 percent. Okay? And in Rademacher 2 moves, the two new crossings are both 0 crossings, or they are both 1 percent. Whatever I take here in my meridian M. And I take the loop from the overcross, which goes from the overcross to the undercross, and do that. So it's linked with the meridian. So this is a 1%. On what we construct one cycle which can make singular only 0 crossings. So that means we use the meridian. Construct one cycle which makes singular perhaps not always. But singular is for some Rademacher moves 0. Never 1%. Okay. Which makes I have to erase that. So we will define the weight for the distinguished crossing. So earlier we have seen. So there are two global types of crossings. So they're both positive, 0 crossings, 1 crossings. So okay, there are also, of course, a global type of Rademacher 3 moves. Global type. I have to tell you that. I have already said you that this here was the type R. This here is the type L. And we could have the point at infinity here, we call it A, could be here B, or it could be here C. A, B, C. So A, B, or C is infinity, okay, or base point. So there are different possibilities for the base point. Also something I have to close there. So different possibilities for the base point. So we have exactly 6 global types of Rademacher. So this is the distinguished crossing, which I make always with the Sika error to better visualize it. And we have the crossing ML. So we see this D is the 0 crossing. If and only if the type is RA, RB, or LB. And we will also use the crossing ML. ML is the 0 crossing. This is the crossing ML. It's a 0 crossing. If and only if it is RA, RB, LB, LBs, or LCs. So it turns out we will never use the LB for MN. Forget about it. So that's it breaks some symmetry. Always good. And we define a weight. So let D be a 0 percent. So here 0 percent in our.
Excuse me, how much time do you need to finish?
Oh, I think an hour or two, but I will make it short. Okay. I will just go up to the definition of the one concept. I think I'll stop there. So here is the point at infinity because it's a 0 crossing. This is 0. So we call an F crossing. F crossing is a 1 crossing. F crossing. F crossing. F stands for foot. F crossing for D is a 1 crossing with the foot in the open arc from infinity to the overplot of D. So, what are the F crossings? This here would be an F crossing. It can be designated. It could be a crossing IHN, for example, like this, to the type IE. Could be go like that, and it could go like that. Okay, these are all F crossings. So if the one crossing has done that, not. Because the foot is not at the in this open arc. From here to here. Okay, this and we define a relative finite type invariant of degree 1 with respect to the Reidemeister move. So we define V1 of D. It's a sum of VQ of Q as constant. For it. Okay. We make the same thing V1 of ML. Same. If ML is a zero crossing. In any case, I have no time to make a proof, so I can erase it. Crossing. Okay, these are our weights. These are our weights. So we have the global types. Okay. Reidemeister 2, I haven't heard anything about Reidemeister 2. Reidemeister 2, this is always the sign plus. Here. And we consider only Reidemeister 2 moves, no matter the orientation of the branch, where these are zero crossings. You know, this is zero crossing. Okay. And so we take both of these divs, we look like that. It is now a double error. Plus minus, okay. Yes, infinity is zero crossing and F crossings are separately defined. It cannot go to this case cannot happen, but it is exactly the same. So we have a variance of D2. So let me define the one foot cycle. L X I define a one foot shape, okay? X of S is it's C1 of M, H0 of M plus the coefficient H minus plus H minus okay, it's defined as the following way. So as or see, these are not diagrams with just one ordinary double point with positive sign, one ordinary double point with negative sign. And these are, of course, because I write H0 means that the isotope. So it's defined as the sum over all P and S, which are global type A and C. So we have defined global types. Sin P times x to the power V1 ml plus VHM, it's a rise of HM minus 1 over 2 plus 1 minus x V1 ml plus VHM minus 1 over 2. It's just about the 1. The ml singular division. So it means on this Reidemeister move, we make ML singular. It doesn't depend on the side, because we have all seen it's the same thing. ML singularization, and which has the sign which comes from the sign of ML. If ML was positive, it's a double point of positive sign. It was negative, negative sign. Plus this. Plus some VS, which are of type RA, RB, LB. Here we have some P. The right of D, x to the power of V and V1 of D. Here, desingularization positive side.
Well, can we? I think the time is over, more or less.
Yeah, I've just finished the definition. So this
Okay.
and then wird dann DNS R2 with zero crossings signed with x to the power of 1 of d and a singularization of positive crossing minus singularization of negative crossing. I don't know if it's more here. And the theorem is 1%. It's a 1%. And we can apply all the machinery, the tangle equation, and so on for that. So sorry for that. I'm a bit over time. There's still lots of things to say, but I think I have to stop here. Thank you for listening to me.
Very wonderful talk. Very thank you, Professor Fiedler. Okay. I very want to read your paper about these topics. I think it is very deep and very insightful topic about the knots theory and one cocycle.
Yes, there are some material which makes the techniques in place. Is mono.
And I can see that it's very big job.
That's a little bit technical, but then it becomes all combinatorial. And so there are now 3 papers which I mentioned at the beginning, which are in preparation. They are more or less finished, but it's always missing the computer program. So the point is to get something interesting, one really has to add the longitude. And then the number of Rademeister moves. Okay, for a computer, it's nothing, but for a human, it's much too hard. So I couldn't calculate any examples by hand. So, but what has Boolean programmed makes optimistic there is something in it. So what it will be, we really have to wait that the computer programs will tell us. So
actually very actually interesting that recently I have written a paper. I also focus on the tree sequence. Actually, it is about a triple point, and I used the tree sequence to construct a quandle structure. I call that a second quandle. I think there may be some very deep connection between the works with you. I'm very hopeful to communicate with you. Very thank you for the Professor Fiedler to give us this great talk. So I think today we need to end this talk, and maybe you have some time you can send email to us. Very thank you. Okay.
Just write me and I will send you the newest version when I have it. Okay.